Hello friends, welcome back once again. This is Nagaraj SK, lecturer of Computer Science and Engineering Department, Jain Polytechnic, Belagavi. So here I'm going to complete your Unit 6, that is Grady Technique, with lecture number 52. So here I'm going to brief you about Dijkstra algorithm. That is the last topic from your 6th unit. So I'm going to brief you about this Dijkstra algorithm. What is Dijkstra algorithm, pseudocode of that Dijkstra algorithm, and how it works, and all with examples. So we'll begin for Dijkstra algorithm. So Dijkstra algorithm, and especially in this section we consider the single source shortest paths problem for a given vertex called the source in a weighted connected graph, and find shortest paths to all its other vertices. And it is very important to stress that we are not interested here in a single shortest path that starts at the source and visits all other vertices. This would have been a much more difficult problem. Actually, a version of the traveling salesman problem introduced in the previous sessions or previous slides, and discussed already we discussed that salesman problem, right? So the single source shortest path problem asks for a family of paths, each leading from source to a different vertex in the graph. Though some paths may of course have edges in common, a variety of practical applications of the shortest paths problem have made the problem a very popular object of study. The obvious but probably most widely used applications are transportation planning and packet routing in communication networks, including the internet. Multitudes of less obvious applications include finding shortest paths in social networks, speech recognition, document formatting, robotics, compilers, and airline crew scheduling. In the world of entertainment, one can mention pathfinding in video games and finding best solutions to puzzles using their state space graphs. So, there are several well known algorithms for finding shortest paths, including Floyd's algorithm, you might have heard. For the more general all pairs shortest paths problem, we'll be discussing in the later stages. You will be learning those in your higher studies. So here we consider the best known algorithm for the single source shortest path problem called Dijkstra algorithm. So this algorithm is applicable to undirected and directed graphs with non-negative weights only. Since in most applications this condition is satisfied, the limitation has not impaired the popularity of Dijkstra algorithm. So the Dijkstra algorithm finds the shortest paths to a graph vertices in order of their distances from a given source. So first it finds the shortest path from the source to a vertex nearest to it, then to a second nearest, and so on. In general, before its ith iteration commences, the algorithm has already identified the shortest paths to I-1 other vertices nearest to the source. And these vertices, the source and the edges of the shortest paths leading to them from the source from a subtree Ti of the given graph. So here the graph is used to represent the distance between two cities. Everybody is often interested in moving from one city to other as quickly as possible. The single source shortest path is based on this interest. So in single source shortest path problem, the shortest distance from a single vertex called, that is source, is obtained. So let G of v comma e be a graph, then in a single source shortest path, the shortest path from vertex v naught, that is v0, to all remaining vertex is determined. The vertex v0 or v naught is then called as source, and the last vertex is called a destination. And it is assumed that all the distances are positive. Then we have a pseudocode for this Dijkstra algorithm, that is it is taking a graph and as argument, as input, and a vertex S as a source vertex. So the Dijkstra of g comma s indicates it is a function that Dijkstra algorithm for single source shortest paths. Then what input we are passing is, as I told earlier, that is a graph G, which is consisting of vertices and edges with non-negative weights, and its vertex S. And what output we are going to get from this, the length dv of a shortest path from es to v, and its penultimate vertex pv for every vertex v in v. So initializing q, that is with the help of initialize priority q to empty. So for every vertex v in v, dv is set to infinity, because we don't know the value of the traveling cost from one for all the vertices from source to destination, and initially pv is set to null. Insert q comma v comma dv, that is initialize vertex priority in the priority queue. Then update priority of s with ds, that is ds is initially 0 and decrease q comma s. So initially if it is null, for I equal to 0 to n minus 1, that is v minus 1 do, that is number of vertices minus 1. Then u star delete the minimum priority element from the given graph. So vt is set to vt union of u star, that is for every vertex u in v minus vt, that is adjacent to u star. Then do these operations. What operations? Before that, doing those operations, we have to check one condition, that is if du star plus weight of u star comma u less than du, then du is equal to du u star plus weight of u star comma u, and pu is set to u star, and again decrease the graph's edges, that is q u comma du from the given graph. So this is how the pseudocode of Dijkstra algorithm looks like, and the working of that, as I said. Then for example, if you apply the Dijkstra algorithm for this graph, it is consisting of 5 vertices and 1 2 3 4 5 6 7 edges, right? How many edges are there? 1 2 3 4 5 6 7 edges are there, and 5 vertices are there. So we'll apply Dijkstra algorithm for this graph and check what kind of minimum spanning tree we get after applying the Dijkstra algorithm for this graph. So at the very first stage, we have to select an edge. That edge we are going to select is from a to b. So we are setting a as the source. So from a to b, so we are selecting here a as the, we are assuming that it is good idea also. A, B, C, D alphabets are there, so we are selecting A as the source vertex. We are assuming the A as the source vertex. From source vertex which all other vertices are connected through the edges, and from that we have to select minimum edge. So from A to B is there, from A to D is there, right? So from A to B is there, A to D is there. Among these two, the weight of minimum weight is 3, so that we are selecting. The length of that A to B is 3, then that edge we are selecting. Again from B and A, among these two, B to D is there, B to C is there, and A to D is there. So A to D is 7, then B to D is 2, then B to C is 4. So among these three, B to D is the smallest one, so we are going to select A to B, B to D, that is of length 2. So that is the next edge we are selecting. So A to B, B to D. Then from B to C is there to travel from C vertex, and already we visited this D vertex, and from B to C is remaining and E is remaining. So from D to C is 5, B to C is 4, then D to E is 4. So among these three, B to C is 4, that we are selecting. That is, we are going to select from A to B, B to C, right? That is of length 4. That edge we are selecting, this one. Then and finally only one edge, only one vertex is remaining from that is E. So how to travel to E, right? Through what vertex we can travel to E? There are two ways. We can travel through D or we can travel through C. So among these two vertices, which edge is having less value, less weight, that we need to check. So we are having here D2 is 4 and C2 is 6. So among these two, D2E is the smallest weight. So that is the reason we are going to select D2E. So finally the minimum spanning tree will look like this. That is A to B, then B to C, then B to D, then D to E. This is the minimum spanning tree of this given graph. So this is how it will be traveling from source vertex to destination vertex. Then analysis of Dijkstra algorithm is the time efficiency of this Dijkstra algorithm depends on the data structures, what data structure we are using for managing this. So implementing the priority queue and for representing an input graph itself. So here it is implementing the priority queue and for representing an input graph itself. So what formula we can use is big O of number of vertices square plus number of edges equal to big O of number of vertices square, that is V square, where E stands for edges, V stands for vertices, then function of edges, then function of vertices, and big O, that is constant. Then let me summarize what we discussed so far. So we understood what is Dijkstra algorithm, then the pseudocode of this Dijkstra algorithm, and examples and the analysis of Dijkstra algorithm. If you are having any doubts in this, please do ask your queries. Definitely I'll be helping out for your queries, and don't hesitate to ask your questions. Not only in this session, if you are having any doubts throughout this design and analysis of algorithms subject. If you are having any doubts, please do ask your queries and I'll be helping you out definitely. So thanks for watching. Thank you so much.